Okay, this is lab one. This is estimating the amount of excess charge on a piece of tape. The objectives here were to estimate the amount of excess charge on a piece of tape using some really large order of magnitude estimates. This estimate is in terms of the amount of electrons that actually had to move between tapes to produce this charge. Some of the physical models that we use to underlie all of this are the stuff we've learned in lecture, Coulomb's law, and older stuff like law of gravity. And as a preview of our results, we learned that only a really small fraction of the atoms need to actually move electrons around to produce a force that's macroscopic that we can measure. Okay, some of the models are here in more detail. There's Coulomb's law, there's gravitational force, and the assumptions that we're making when we're using tapes like this are that they all have equal charge because they're manufactured in the same way, and we are making a spatial assumption about where the charge is located. We're saying that it's equivalent to a point charge located at the center of the tape. So, one experiment which we do in this lab is to float a piece of tape over a charged piece of tape. The system in this example is the floating tape, which we call tape B. U-tape is the name that we give to the charged tapes. The surroundings here are Earth to provide gravity, and then tape A, which provides an electric propulsion. It comes from the bottom, so we are expecting gravity and the tape to oppose each other. And in this condition, in this initial condition where they oppose each other, we're saying that the force of the charge equals the force of the gravity, and that they are suspended at a separation d, which we'll measure. Okay, how do we create these tapes? The first thing that we do for any of this experimenting is create the tapes as per these pictures. We stick one on top of another, and then hold it by a tab at the end, and then pull. This strips electrons off of one tape and brings it to the other. It's very important that you only handle these by the tab so that nothing discharges accidentally, and you do actually maintain some charge on the tape. Once you have these tapes, we can ask some questions about how they'd interact with the world. One such question is, what happens if you bring two of the same tape together? And because we're assuming that they have like charges, we are expecting them to repel. That is what we observed. If you bring two together, they don't want to be next to each other. Another question is, how might charged tape interact with a neutral object? And we expect a much stronger attraction to a neutral object just because of induced charges. The neutral object might have no total charge, but electrons in it might be free to move around and polarize such that one surface of the object has a slightly different charge than the other, as induced by the tape, which would produce a very small attraction. Okay, another quick thing we did just to test out with these charged tapes is to create a known charged object, like a pen, and then observe how it interacts with our charged tape. We rubbed a pen against our hair, which we expect would produce a negative charge because electrons are stripped from the hair and end up on the pen. And then we can ask some questions about what would happen to the tape under certain assumptions. What would happen to the pen in the tape given certain assumptions about the tape? If we assume that the tape is positive, then we should expect that the negative pen and the positive tape attract. Other way around, if not, and if the tape somehow didn't have any charge, if we made it wrong, there should still be a much weaker attraction. But luckily we just observed decided attraction, so we can conclude that there is a positive charge carried by the tape. Okay, now we can get back to the floating tape part. This is the experimental setup. We have one tape floating against another at a separation distance d. We have this initial condition in equation form. The force of gravity equals the force of the electric charge. And then we have a couple measurements that we're making here about the floating tape itself, the system, which is tape B. There's the length of it, the width of it, and then the distance between tape A and tape B. We can use these to do some calculations. Again, some of the assumptions that we're using about the tape itself is that there's only one atomic layer providing any charge, and it's uniformly packed, and that all tapes have equal charges. This is some measurement that we had about the tape to begin with, its density. This is the length of the piece that was actually floating, and we use this to calculate the mass of the tape, and then the force of gravity, which ends up being about 2 times 10 to the negative 3 newtons. It's pretty small. Then there is this balance analysis. We know that the separation distance was measured to be about a centimeter. Using this condition we described earlier in Coulomb's law, we can solve for the total amount of charge that's required to hold the tape at that height, which is about 5 times 10 to the negative 9th coulombs. So from that we know that the amount of electrons that can contribute to that, that are needed to contribute to that, is about 29 billion. It's a lot of electrons. But as a fraction of the total electrons that are part of that uniform layer, it's actually pretty small. The 29 billion is only about 8 times 10 to the negative 8th of the total electrons, which is about 1 in 12.5 million. 1.12.5 million atoms actually lost an electron to produce the positive charge of the tape. Okay, So a little bit more discussion. Observing the tape taught us some things about the electrostatics of opposing charges and attracting charges. There were a couple limitations that we should talk about. We had assumptions that really drastically simplified our setup, like the point charge model, and we also ignored factors like humidity and maybe accidental discharges that affected the total charge of the tape. But in conclusion, we did still manage to see some macroscopic forces from what we calculate to be really microscopic changes in the charge of an object. Even though they only carried about 10 to the 10 excess electrons, we observed a very measurable force from that. That's all. I think we're done. Thank you for listening.